So there was a request for another electronics example. And no good deed or question asked of a professor goes unpunished. So, let's do this. It's called a bridged time delay equalizer circuit analysis. It's got 3 inductors and 2 capacitors. For those of you keeping score at home. So, should be a good time. It's actually not terrible. It could be worse, but this is pretty long. So let's get started. First, we need to do the linear graph, right? And our linear graph for this is going to be, there's going to be a node here, a node here, a node here, a node between here, and then we'll take this to be the ground node. So ground, and then we've got this middle one, and we've got this top one, and then we've got the left one, and we've got the right one. These are all our nodes. And let's see, we've got the source connected up here, the voltage source, Vs. And we've got L1 connecting that node to this node. Maybe I'll go down with that. L1. And then we've got L2. We can go arbitrary directions here, but let's do that. L2. Let's go C2 and L3. And then we've got the capacitor 1, C1 here. Okay, so the output voltage is going to be off this node here, V out. And that's our linear graph. So, well, 1A is the normal tree, right? Which let's use green for. I see an across variable source, Vs. That'll be in our normal tree. And then we see A-type energy storage elements. So there's C1, there's C2. We're not yet done, though, because we can take one of these inductors without creating a loop. We can choose it arbitrarily. I will choose L3 as being the one that'll be in the normal tree. Now if I select anything more, it's going to create a loop, and so I'm done with the normal tree. Great. So now I've got my normal tree. I'm ready for my primary variables. My primary variables are cross variables on branches. So I've got Vs, I've got Vc1, I've got Vc2, I've got VL3, and then I've got through variables on links. So I've got IL1 and IL2. Secondary variables. The current that the source delivers, the current through C1, current through C2, current through L3, voltage across L1, voltage across L2. State variables. So they're the across variables on A-type branches. We've got two A-type branches, C1 and C2. So we've got state variables VC1 and VC2. And through variables on links, so we have IL1 and IL2. Now, something kind of funny happened here, didn't it? We didn't end up including the current through the inductor L3 as a state variable, just so. And that was because it ended up being a branch in the normal tree. That happens occasionally when there is an energy storage element that is dependent. Okay? It's not an independent energy storage element. So we only have a fourth order system for state variables in this problem. I think that the question here was first.
The nodes and ground are still in the normal tree, right?
They are, yeah. I just get a little lazy sometimes and don't want to. Yeah, they're always in the normal tree.
Okay,
Yeah.
just making sure.
Yeah, excellent.
That was exactly my question.
Oh, perfect. Love that. God, there's a new thing. I fed two birds with one hand.
What?
Okay.
That's what you're supposed to say now instead of killing two birds with one stone. Because
There's many ways to
vegans.
skin a cat, so, you know.
Yeah, because vegans.
But now you can feed a cat with one knife.
Okay, so we have like a Game of Thrones, Jon Snow kind of plot happening here. Is that what's going on?
Like, most of the people in the Night's Watch die, so can we not, like, use that metaphor?
Well, I was referring to with Jon Snow. And the knifing.
I watched the same episode of that show.
Wow.
Skip season 7.
Jon Snow dies, but does he?
I don't know.
And then he
Yeah.
comes back.
No reason to watch.
If it's a spoiler at this point,
Yeah.
like you got no right to complain.
And it was all a dream.
So n was equal to 4, right? So you have a fourth order system. We have 5 energy storage elements. It's only a fourth order system. That's because one of them is dependent. So
We get to choose which one's dependent.
that's right. So we could have chosen that any of these three was the dependent one. Actually, no, we couldn't have chosen L1. L1 is definitely independent. No, wait, L1 could have been. Yeah. So we could have taken any of the three.
I'm a bit confused on the whole dependent independent thing.
Yeah, so their A-type and T-type elements are energy storage elements, right? So when they show up in an independent way, that means that they'll have a state variable associated with them. So that means that an independent A-type will show up as a branch, and an independent T-type will show up as a link. But if you have a dependent T-type, it shows up as a branch. If you have a dependent A-type, it shows up as a link. Great. Yeah?
What's going on with V naught? Is that a node?
It's a node. That's the output voltage that we're interested in. So at the end, when we write the output equation, we're going to want to write an equation for V naught. That's why I drew it up there. Finding the state equation has no relevance to that. At the end, when we write our output equation, that's when we're going to want to know what V naught is. Yeah. Very good. So, yes?
So you do the process the same, just reorder it,
We'll do the process the same. At the end, when we do our output equation, we'll write down V out as our output, and then we're going to need to rewrite that in terms of state variables and inputs. And when we do that step, then we're going to have to figure out what V out is in terms of these other variables. Yeah.
So there's a contour around it, you have to rewrite it based
Well, actually, what we'll do is we'll look at a a KVL equation or a compatibility equation, we'll say, okay, the voltage at this node has to equal the negative voltage across C1 plus the voltage across Vs. That's what we'll write as our output equation. So it's coming. Stay tuned for more. Okay. So we have 1D, which is the vectors. We've got a state vector. We can list these in any order we want, but we just have to stay consistent after this point. So VC1, VC2, IL1, IL2. Our input, we only have one input, right? Boring. Just Vs, or one vector. And then our output, we're going to just call it Vout for now. And we'll return to that when we write that in our standard form at the end. Okay, 1E, that means we're ready for those elemental equations, right? Okay, so we've got a capacitor, C1, C2. We've got 3 inductors, L1, L2, and L3. We've got dVC1 dt equals 1 over C1 IC1. dVC2 dt equals 1 over C2 IC2. We have dIL1 dt equals 1 over L1 VL1. We have dIL2 dt equals 1 over L2 VL2. And then we've got dIL3 dt equals 1 over L3 VL3. VL3. Yes?
Can you like scroll back a little bit to see if I got it right? I'm a little bit confused about what happened to IL3. Oh wait, no, it's voltage. Never mind.
Yeah, VL3. Yep. Good. Those are our elemental equations, and now we're ready for our continuity equations, right? Continuity. Let's continue with this like tabular way of doing things. So let's look for a continuity equation for C1. We look back at the normal tree and we say, okay, C1 is a passive branch and we need to draw a contour for it. This contour works. It says that the current going into the contour is IC1 minus everything going out, equals everything going out. So IC1 equals negative IL2. IC1 equals negative IL2. Okay, so other continuity equations. We can do one for C2 as well, right? So IC2 is leaving the contour, so it's equal to everything going into the contour. So IC2 equals IL1 minus IL2. IC2 equals IL1 minus IL2. Okay, now we've got a continuity equation for L3 that we can write with this contour, right? So that contour is essentially the same equation as the other one, except we have IL3 equals IL1 minus IL2. Great. Oh, but we don't want to write that one there. Let's write it down by the L3 equation, because that's where we're going to plug it in, right? We're going to plug it in to this equation. So let's keep that straight. 1G, compatibility. Okay, so for each of these elements we didn't write a continuity equation for, we'll need a compatibility equation. It's the two links, L1 and L2. L1, when we plug L1 into the normal tree, we get this loop, right? So it says that VL1 equals VS minus VL3 minus VC2. I'll write it up here and then I'll copy it down so that we can look at this while we're writing it. So VL1 equals VS, is it plus or minus VL3? So it's VS minus VL3 plus or minus VC2? Minus. Minus VL3 minus VC2. Okay. So I'll just copy this guy down. And we'll put it in the table, which it should go by the L1. Okay? And now we can do it for L2, which when we put L2 in, it creates this outer loop, right? So we've got VL2 equals VC2 plus VL3, VC2 plus VL3, minus VS plus VC1. Okay. So we'll put that guy down here too. Okay. So this part actually took us less than 20 minutes to get this far. Okay. This actually is a stage at which I'm going to show you a set of tools on Wednesday. It's like an online web app that I wrote with an alumnus from here, Cameron Devine, who's now a PhD student at UW. He and I wrote this web app that allows you to just plug in these equations, elemental continuity compatibility equations, into the web browser, and it'll give you the ABCD matrices. Okay? Yeah.
Second continuity equation down, having a little bit of trouble discerning C's from L's.
Yeah. So
IC2 is IL?
that's IL1. Yeah, sorry. Sometimes it get a little curvy. Should be an L. L1, L2. So yeah, so at this point we could use that application and find the ABCD matrices. It would do the step 2 algebra part for us. Okay, we're going to go through it. It does get a little bit messy in this problem. Not terribly so, but it does get a little bit messy. So we're going to go through it as thoroughly as we can. Be warned that there are some messy steps ahead. But it's just algebra. It's not going to be too bad. Okay. So 2A. The first step is pretty straightforward. We just have these elemental equations we need to rewrite and do these substitutions directly in, right? So this substitution will be the first one. We'll rewrite our C1, C2 table here. So C1, C2, L1, L2, and L3. And we'll rewrite dVC1 dt, which was the left-hand side of the elemental equation up here, equals 1 over C1. Instead of IC1, we'll plug in the continuity equation here. So it'll be negative IL2. So we use that guy. Now we're going to use this substitution here to get rid of IC2. So we'll get dvc2 dt equals 1 over c2. Instead of IC2, we'll do IL1 minus IL2. Yep, so we got that one. Now we'll plug in the compatibility equation for L1. So we've got dIL1 dt equals 1 over L1 times, it's going to be Vs minus VL3 minus VC2. Okay. The next one is this longish one. So dIL2 dt equals 1 over L2, and instead of VL2, we plug in VC2 plus VL3 minus VS plus VC1. Okay, check. Now we've got this last continuity equation to plug in. And that one says dIL3 dt equals 1 over L3 instead of VL. So we're plugging in for IL3, not VL3. So we need to rearrange this and do the substitution, right? So VL3 equals L3 times, instead of dIL3 dt, we're going to do dIL1 minus IL2 dt. Okay? Which, of course, expands to be L3 dIL1 dt minus dIL2 dt. Okay. So now we've got 5 equations here. We're down to 5. We need to get it down to how many? 4, because the order of the system is 4 state variables. So we have 5 equations. One of these variables does not belong. Which variable do we need to eliminate?
L3.
Specifically the voltage across L3, right? VL3. So this VL3, and it shows up here and here, needs to be eliminated. So we can do that by direct substitution here, right? No problem. Yes?
Wouldn't it be better to just plug the DIL1 and DIL2 into the VL3 equation? Because then all the DIL over DTs distributed.
Yeah, the trouble is that we lose then our state variable equations. So we want to maintain the equations that have, so we want to get rid of VL3. And if we do that substitution, we don't get rid of VL3, it's still one of our variables. And we lose access to some of the information about IL and IL1 and IL2, which are our state variables. So we need to keep the IL1 and the IL2 variables around. And we got to get rid of VL3.
Okay.
So in terms of simplification of this set of equations, you're right. That would simplify them. You just wouldn't end up at the place that you want.
Okay.
You'd have a simpler set of equations that are not your state equations. Okay, so we can do that substitution. So 2b. Let's look for a moment here and look at these first two equations. VC1, IL2, both state variables, right? So we don't need to do anything to this equation. It's already a state equation. This equation, VC2, IL1, IL2, it's already a state equation. It's just the L1 and L2 equations that require us to do this substitution to eliminate those variables. So let's focus there. Let's say, let's plug in the L3 equation into the L1 equation and the L2 equation. And it's going to get kind of big and expansive, but let's do it, and then we'll see what we've got, okay? So for the L1 equation, we've got, so we'll do L2 as well. The L1 equation, we've got DIL dt, DIL1 dt, equals 1 over L1 Vs minus, plugging in for VL3, we have L3 DIL1 dt minus DIL2 dt. And then we've got minus Vs plus, no, sorry, we have minus VC2. I skipped to the other equation. Minus VC2. Okay. In this equation, we've got DIL2 dt equals 1 over L2. And then we've got VC2 plus L3, substituting again, DIL1 dt minus DIL2 dt minus Vs minus or plus VC1. Okay. We've succeeded in getting rid of the non-state variables and inputs. However, solving them for the time derivatives of the state variables is a little bit problematic because we've got these time derivatives of the state variables on the right and left hand sides of these equations. If we just had the IL1 dt on this side, we could simply add that one over, factor out DIL1 dt, and divide by what's left. But we've got a DIL2 dt in here as well. Okay, so these are coupled equations. Bummer. Okay, so unfortunately, in many cases, we get this substitution, and for simple problems, we don't need to do any complicated algebra to solve for those time derivatives of the state variables. In this one, we do have to do more, and it's, not awesome in every sense, but it's okay. So what we're going to do is we'll rewrite them. First of all, we'll bring the IL1 and combine it with this one first, just to get that out of our way. And then we'll do this same one here, and then we can essentially solve for one of them in this equation, eliminate it in the other equation. It's a little bit messy, but it's doable. Okay? So let's rewrite this. I'll just keep writing them as L1, L2. So let's bring the DIL dt over. So, and let's do it in one step because we're really good at this. DIL1 dt equals. So I would add L3 over L1 dIL dt to both sides, right? I would, this one would go away, I'd get one over here. Then I could factor out dIL1 dt. I could divide over whatever is left from that factoring process. What's left is going to be 1 plus L3 over L1. So what I'm going to get is 1 over L1 times 1 plus L3 over L1. And then I'm going to have my Vs minus, but this is actually going to turn into a plus here now, right? L3, I still have my dIL2 dt minus Vc2. Okay, this other equation, I can do something very similar. dIL2 dt, I can bring the dIL2 term over. I can add L3 over L2 dIL2 dt to both sides. I can factor out the dIL2 dt. What's remaining is 1 plus L3 over L2, and so we'll divide that over. So we get 1 over L2 times 1 plus L3 over L2 times Vc2 plus L3 dIL1 dt. And we've got my minus Vs and plus Vc1. Okay, so we're getting there. One thing we can do is if we want to eliminate one of these in the other, all we have to do is plug in one into the other, right? So you plug the dIL1 dt expression in here, and we're home free, right? Just got to simplify. We can plug this L2 equation into here, and then we're home free. We just need to simplify. I am going to do that. I'm going to say L1, so this new L1 equation into L2, and the L2 equation into L1. And then we're going to rewrite our state equations, and I'm not going to find out what the coefficients are. It's a little bit messy, right? But I'll write them in general, and then we'll put them into our standard form, okay? I'll assume that you guys can plug this in and simplify it down. It's just a little bit of combining Vc2 terms, etc. So what we're going to end up with is we've got our C1, our C2, our L1, our L2 equations. And so remember, our C1 equation was already a state variable equation. It was just dVc1 dt equals negative 1 over C1 IL2. So actually these first two equations are identical, right? In the interest of time, I'm going to do this cheating thing where I just copy them down. You guys can draw an arrow. And then what we're going to have for the L1 and L2 equations are dIL1 dt equals, I can just look at this and see, I know that there's going to be some term times Vc1. So I'm going to call this, I'm going to give this a name. I'll call it alpha times Vc1. I'm going to call, and then I'm going to say, actually I'll call it alpha 1. Alpha 1 Vc1. I'm going to call plus beta 1, and then this is going to be Vc2. There's also a Vc2 term in here. Plus gamma 1 times IL1 plus some delta 1 IL2 plus lambda 1 IL3. Or no, there's no IL3. Oh, lambda 1 Vs. Okay? This other equation will look very similar, right? dIL2 dt is going to have some other alpha, so alpha 2 Vc1 plus some beta 2 Vc2 plus some gamma 2 IL1 plus some delta 2 IL2 plus some lambda 1 Vs, or lambda 2 Vs. So here are our state equations, where these will give you the alphas, so the alpha I, the beta I, the gamma I, the delta I, and a lambda I. Okay? And here we go. So now I need to do 2c, which is the standard form of the state equation. So it's dx dt equals the A matrix times the x vector plus the B matrix times the input u vector. And what I've got here is my dx dt is, so I'll just put d dt because it's time derivative of each of these x vectors, so each of these x variables. So we've got vc1, dvc2, dil1, dil2, that was our state vector, equals, the A matrix has got to be a 4 by 4 n by n matrix, right? And we've got the x vector, of course, here. vc1, vc2, il1, il2, and I've got the B matrix, which is a 4 by what? Because it's got to multiply a 1 by 1, right? Vs. It's got to be a 4 by 1. So now I just need to fill in these rows, right? The first equation gives me dvc1 dt equals 0 vc1, 0 vc2, 0 vc3, negative 1 over c1 il2, and 0 vs. The dvc2 dt equation gives me 0 vc1, 0 vc2, 1 over c2 il1, negative 1 over c2 il2, and 0 vs. il1 equation gives me alpha 1 vc1, beta 1 vc2, gamma 1 vc or il1, and delta 1 il2, and lambda 1 vs. Similarly, il2, it's got alpha 2, beta 2, gamma 2, delta 2, lambda 2. Okay. Very good. We've got our state equation in standard form. Great. 2D. We need our output, which is V out. We need to write it in terms of state variables and input. So way up here, we had the V out is the voltage associated with this node. We could think of there being a sort of virtual connection to ground here, right? Every voltage is referenced to ground unless it's referenced across an element. So the voltage here is actually the voltage from here to ground. So all we have to do is find a path to ground and add the voltages to that on that path. So from here, we go, what we say is that this is equal to Vs, so the Vs would be positive, and then a drop across C1. So Vs minus Vc1, or negative Vc1 plus Vs. So we write V out.
There's obviously like a best way to do it. If
Yeah.
we go like L2 to L1 to Vs.
Yeah.
Or any other kind of crazy.
So you could do it any way you want. Then you'd have to take those variables and write them as state variables and inputs. I chose this path because Vc1 is a state variable and Vs is an input. So I'm done. If I had gone this route, in here and down here, I would have had VL2, not a state variable, VC2, which is a state variable, and then VL3, which is not a state variable. So I would have had to eliminate those. I didn't want to do the extra algebra. So I chose the route that got me there with state variables and inputs. Yeah?
I'm just scared of the algebra because setting it up is, I'm not going to say fine, but I think I can get there. But
Yeah.
a lot of this, I know for a fact, if I do this on my own,
Yeah.
I'm going to get something in that algebra.
Sure, and that's part of why I really encourage you to use these computer algebra systems. And the one that I'll give you on Wednesday to do the details of the algebra here, it is built on a Python package that you can use to do the same thing. So you could do this not in the web browser, you could do it in, on your own thing. But this web app is pretty nice. It'll let you save your file too, so you can save it for later and edit it. If you mess something up, you can edit it again. So it's pretty nice. So we showed that V out is just Vs minus Vc1, which just leaves the last step, which is to write the output in standard form, which is y equals the C matrix X plus the D matrix U. And for us, that is y, or we could write it as V out if you want. V out equals the C matrix, which has got to be a 1 by 4 because we have to multiply the state vector, which is a 4 by 1. And we've got VC1, VC2, IL1, IL2 as our state vector X, plus the D matrix, which has got to come out to be a 1 by, and it's multiplying the input, which is a 1 vector, so it's a 1 by 1. And we just need to fill in this row from this equation here. So you have a negative 1 times VC1. We have a 0 VC2. We have 0 IL1, 0 IL2, and what is the coefficient of Vs? 1. So this and this are the state space model together. The state equation in standard form and the output equation in standard form. Yeah?
So when you put in all those alpha betas,
Yes.
how does you simplify those two equations?
Yeah, that's right. So if you take these two expressions, you plug DIL1 dt into this L2 equation, and if you plug the DIL2 dt into this equation, you'll have a bunch of coefficients of your variables here, and I just called them alpha, beta, gamma, delta, and lambda, because I didn't want to take us through that messiness. It's really not that bad. It's just a lot of writing because there are a lot of terms in the expression. this is a more involved problem than I would expect you to be able to do, in 20, 30 minutes on an exam. But it is the type of problem I would expect you to be able to do outside of class when you've got, time to be able to sit down and work it through on like a homework problem or something like that. This is a real-world circuit. I mean, this is actually used as a time delay. Thanks Wikipedia for the circuit diagram. But you can use this to put a time delay on a signal that's coming in. You can specify that by choosing your L1, L2, L3, C1, C2 according to design constraint requirement. So this is a real-life circuit. There are a lot of applications for this type of thing. And we want to be able to analyze what goes on and come up with a state space model of it, and we've done so. So it's really it's a fourth order system. It's pretty big, but what we're seeing is that really there's no one part that's very difficult. Really, actually, everything up until 2B is very straightforward and always is. Okay, this. Up at this point, all you've done is these substitutions over the continuity compatibility equations. And in fact, we can automate this process of simplifying from this set of equations down to our state equations. We can make that automatic. And so I'll give you guys on Wednesday those computer algebra system tools to do that. And I want you guys to recognize that being able to do this process up to this point is the most important thing. You need to be able, of course, to simplify and do the algebra. I mean, that's an important thing to be able to do. But on a big problem, you're almost always going to want to automate that process because it's so hard not to make a mistake in the algebra somewhere, right? But of course, for a fourth order system, it's something you could do. It would have taken us another 5 minutes probably. And of course, it could be maybe even a 10th order system you could do by hand. But once it gets up to like 40th order, it's getting so big that you'd want to teach a computer algebra system how to do it. So I'll show you guys how to use that on Wednesday. Okay? All right. Good luck in your plots.